Hello and welcome to the Wolfram Language meets Python webinar from Unisoftware Plus. My name is Roman Wahl, and I'm your host for this webinar. At the beginning, I want to get briefly a short overview over our company, the Unisoftware Plus GmbH. We are located in Perg, Upper Austria, close to the beautiful city of Linz. We are currently around 30 employees with 5 theoretical physicists and in the meantime over 20 software engineers. Our main business areas are data science, industrial mathematics, with the focus on simulation and modeling of industrial processes. And we also sell our own financial mathematics product line, which is called Unrisk, to financial customers like banks and insurances. In addition, we are also the Austrian Wolfram reseller. So if you want to buy a Wolfram product in Austria, you will buy it from us. We have all Austrian universities under contract and also the Fraunhofer Gesellschaft in Germany. We will support you with license and installation support from the order of Mathematica until it finally runs on your machine. And if we can, we will also support you technically using Mathematica as good as we can, because we are not experts on everything. And last but not least, we also have consulting and project partnerships in data science projects or Wolfram technology related projects. If you want to get more information on that, just contact us at office@unisoftwareplus.com. So the main topic for this webinar is Wolfram Language meets Python. This coin has two sides. We can, on the one hand, we can use Python within Mathematica with the external evaluate function. And on the other hand, we can also use Mathematica or the Wolfram language within Python with the use of the Wolfram Client Library for Python. And the third part at the end I want to show you how you can use the Wolfram language directly out of Jupyter with Jupyter and Jupyter notebooks. So this webinar will be about the basic principles of how Mathematica can interact with Python, or Python can interact with Mathematica. So the first part is how we can use Python out of Mathematica, and for that we use the external evaluate function. This function was introduced in version 11.2 in 2017 and is still marked experimental. It's not only for evaluation of Python expressions, but also you can also use it, for example, for Node.js, Julia, Ruby, R, Java, Octave, Shell, or SQL database connections. And the syntax is quite simple. The function is called external evaluate. The first argument is the evaluator, which in our case will then be Python. And the second argument is the command you want to evaluate, and this is purely a string, so it's a string-based execution framework in the end. Sorry, that was the wrong slide. So what are the requirements for Python? First of all, you have to have Python installed on your machine. On macOS and most Linux distributions, this is installed by default. On Windows, you have to install it by hand. And you have to install the pyzmq package, which is used for communication with Python over the CMQ sockets. You can do this with the Python package installer pip. Just execute pip install pyzmq, and that's it, more or less. If you need more details, I've put in here a link to the Wolfram reference page where you will be guided through the installation process for each of the operating systems, Windows, Linux, and macOS. So if everything worked out fine in the end, you can then call external evaluate a string, the external evaluator, which is in our case Python, and the command in this case just 2 plus 2. Wait, let's delete the output. So and if everything works out right, then Python will calculate the correct result, which is 4, and it will automatically be converted in the correct Wolfram language object, which is in this case a numeric integer 4. With the use of the greater symbol, you can get an external language input. So if I just type the greater sign, Mathematica enters a new cell, which is an external language input cell, which defaults to Python. And here you can change the language you want to input. This only works only if the language is correctly configured in the background, which we did already for Python here. So within this input cell, you can then now execute any Python commands you like. Here we are just import the Python module math and calculate the square root in the range from 0 to 9 for each number, and I will get back a Mathematica list with the numerical values of the square root from 0 to 9. I can even define functions in Python and use them in Mathematica. So here I define the function f, which just returns the x, which just returns x squared, and store this in the variable f in Mathematica. So I get back here an external function object, and if I now try to calculate this function f with the argument 0, I will get an error message due to the fact that since I'm using here the string Python, the command I execute within Python will be executed in a session which will be ended directly afterwards. So the definition up here is not present anymore when I execute the line f, the function execute the function with the argument 0. What I have to do is I have to start an external session which is kept alive until I close it. For that, there is the command start external session with the external interpreter Python, and I store the external session object in the variable session. And instead of now specifying as a string the external interpreter, I will just use the session object, and with this, everything which I execute within the Python session will be stays alive until I, as I said, close the session. So I can define this external function in Python and use it then like a Mathematica object. A few other nice features, as I already said, this is a purely string-based execution framework. So the only thing you can execute are strings of Python commands. But what you can do, you can evaluate multiple lines of code through Python lists, like I did here. So here's the same command which was up here, import math and then calculate the square root. Now it's put in a list. So first I import math and then I do the square root calculation on this range from 0 to 9, and I get back a list of lists, and in each element of the list is the return value of the Python command. So import math returns nothing because it's just importing this module math, and the calculation here returns back this list of items. Many Python types are natively mapped back to Wolfram language expressions as long as it's possible. For sure, it's not possible for every Python object, but for example here, if we return a datetime object, which is somehow standard, you can Mathematica maps it back to a Mathematica data object. You can use how you get variables into such string templates. What you can use are inline template expressions. So in this string, this is a template expression, and on evaluation of this command, x will here be replaced by the current value of x, which is defined up here, which is 42. So here we should get 43 out. One nice feature for debugging is the use of epilogue. Beside the interpreter you want to use, you can, in this as a list, you can supply different values, such as session prologue, where you can define the starting of some values, for example. So this will be executed before any commands here will be executed. With the prologue, the prologue will be executed every time before a string of an Python string will be executed, so a Python command will be executed out of this list, and then the epilogue will be executed every time afterwards. So with this, you can really do some kind of debugging if you have multiple sophisticated Python steps or Python commands in a list of commands. So just to show you, that would be the output. So at the beginning, at the session prologue, we set n to 0. Then before the first command, which would increase n by 3, we print what n was. So this was n was 0. Then 3 were added, and in the epilogue we also reprint what n actually is, which is 3. And this just iterates over all items of the list. So yeah, with this you can more or less easily debug, or not easily, but you can debug more or less what you get back from Python and put back in a list of Python commands. Yes, and with this, since it's a purely string-based execution framework, yeah, for the beginning, that's all I can show you. And at the end, we should delete the session to our Python interpreter. The other part, or the other side, is how can we use Wolfram language from Python, probably also the more interesting part. The Wolfram Client Library for Python was announced and released to the public in May 2019. It's in addition to the already available connections like JLink and C++. It's fully open source and is hosted on GitHub, and currently in version 1.1. What you need is an active license for a Mathematica product. So this Wolfram Client Library, as we see later, talks to a Wolfram compute kernel or Wolfram controller kernel, more or less. But what you can use if you do not have an active subscription to Wolfram or a Wolfram installation, there is the free Wolfram engine for developers, which is just the Wolfram compute kernel and controller kernel without any user interface, which you can download freely. The only thing you have to do is you have to register it to a Wolfram ID, but otherwise it's free. So one can use this, as I said, just for development. So how does it work? So the Wolfram Client Library talks or communicates over the Wolfram Symbolic Transfer Protocol, which also JLink or C++ uses for communication to a Mathematica controller kernel, for which you need a license, and also for the compute kernels. And the Mathematica controller kernel itself uses the same symbolic transfer protocol to talk to the compute kernels and execute the commands there and receive specs the results. So that's quite a nice infrastructure layout. What do we have to do to get it up and running? As usual in Python, we should use a virtual environment. if you install libraries. So with Python -m for module, vn for the library virtual environment. With this, we create the virtual environment. You just have to specify a name. I chose WCL Python for Wolfram Client Library Python. With this, a subdirectory is created where afterwards all the installed libraries will, everything Python, all the Python stuff will be in. With the command source and the source VCL Python, so that's the directory which was just created, there will be a subdirectory bin and then a script activate in there. With this command, you activate more or less this virtual environment. So all the library stuff is then focused on this virtual environment, and you do not get in conflict with system libraries or anything else. Within there, if you activate it on a shell on Mac or a Linux, you will then have VCL Python in this case at the beginning of the prompt. So you know you are in a virtual environment. And within this virtual environment, you then just type pip install. So you again use the Python package installer pip, and you install the Wolfram client package. This just takes a couple of seconds. And yeah, that's it more or less. To show you how this can look like in Python, I want to use a Jupyter. If you want to Jupyter, just install it again via pip, and you can then run it with Jupyter Notebook. This is a notebook interface in the browser, very similar to Mathematica. Yes, I did this beforehand, and this will look like so you get an overview over the files in your directory where you started the Jupyter Notebook, and I've here the Python Wolfram IPYNB, the iPython notebook. I've already opened it here, and then, as you see, it's quite similar to what you are used to in Mathematica. So let's clear all output first. At the beginning, we have to initialize our session, similar to what we have done in Python. We also have to initialize a session here to the Wolfram kernel, and also a Wolfram kernel has to be started up. So in Python, we load from the Wolfram Client library, from the attribute evaluation, the Wolfram Language session function, and from the Wolfram Client Language, two functions, the WL and WLExpr, which means Wolfram Language and Wolfram Language expression. We will see later on why they are called this way. We can then not really start a session, but we can start a session with the command Wolfram language session, and we store it under session. And if we have a look at it, we see that, yeah, I'm using a Wolfram engine here. So in the Wolfram engine for developers, but it's not started. We have here a red X. You can either start it by hand if you use the attribute start of this session variable, or you just evaluate something. So let's evaluate this command here, where I already used this WLExpr. I will call it now, I don't know, WLExp, and we get back the installation directory of Mathematica and the version. So that you can type this in Mathematica and you will get exactly the same result. So yes, so you see here the version. I'm running Mathematica 12.3, and I'm running on the Wolfram engine. And if I again now look at the session variable, we see that now I have the kernel up and running with the process ID on my Mac of 9657, and here are the TCP sockets for in and out communication. for the Wolfram symbolic transfer protocol, where the Wolfram Client Python library is talking to. And for example, with session.started, I can check whether my session is still up and running and I have a connection to the Wolfram kernel. So basically, how can I evaluate now Wolfram language functions in Python? There are basically two ways. The first is using WL, so Wolfram, I call it Wolfram language. This is more or less a factory of Wolfram language symbols in Python, and you use it you call the attributes of this function WL, and the attributes are just the names of the corresponding Mathematica functions. So for example, the first here, if I want to call the Mathematica function now, which just gives me back the date time when this command is executed, I have to type session.evaluate WL and then just a command I want to execute now. And this gives me back the now command executed from the Wolfram kernel in the background and then converted back to a date object in Python. Another example, if I want, for example, in Mathematica, I would write this. If I want to select all the prime numbers from 1 to 100, this would be select, square bracket range, square bracket 100, and prime q. In Python, it's just session.evaluate, and before every Mathematica command, you just have to write WL dot, and instead of square brackets, you just use round brackets. That's more or less it, and you will get back, in this case, a packed array, which is again a Python object. Yes. Or if you want to just execute the range of 10 in Mathematica, then yes, you can even store this one. So here you get the range from 1 to 10 back from the Wolfram language, from the Wolfram kernel, and you store it in data. So that's a packed array, and you can again use this Python packed array in a Wolfram Wolfram language expression. So here we use the total, the Wolfram function total, and as argument we have a Python object, a packed array, and this is automatically converted to the correct object for the Wolfram language. Then the total command is executed, and the result is received back from the Wolfram Python client library, and then converted to the corresponding Python object, which is in this case the integer 55. The other way of how you can interact with or how you can use the Wolfram language is you can use it directly, and that's actually the same as we have seen. You can use Python from Mathematica, so it's a purely string-based execution, and for this we use WEXPR, so Wolfram expression, and the argument is just a Wolfram expression as string. So here we integrate numerically the square root of x squared plus y squared plus z squared from 1 to 0, and we receive back the result. We even get error messages back if we do something which Mathematica cannot calculate, like divisions through zeros. If you want to have more control over errors, you use instead of session evaluate, you use evaluate underscore wrap. Then the return value is wrapped in a Wolfram kernel evaluation result, from which you can then retrieve the attributes like the message, which is in this case infinite expression power, as we have seen here before, but now you have access to this error message, and you get also, for example, direct access to the result, which is directed infinity. You can even mix both of them, both ways of specifying Wolfram language in Python. Here as an example, we first define a squaring function with this Wolfram Language expression, and we use this Python function then within a Wolfram Language map function, where we apply these squared function to the range from 1 to 5, and obviously this works out well. What we can do in addition is we can define and use our own functions. So here I define the distance between two countries, or more or less the distance between the capitals of two countries. The arguments of this function are two strings, which are the names of the countries. And from this returned is the geodistance between the capital cities in kilometers. So this is also using information from Wolfram cloud servers to get all the information it needs to for calculation. And again, we have now defined this function within the Wolfram kernel, and we can in the next step use this function again in the next step and calculate the distance between Austria and France, so Vienna and Paris in the end, and that's over 1,000 kilometers. We can even wrap these. We can even wrap this function, this Wolfram language function, in a Python function using session.function and then the string name of the Wolfram language function, and assign it to a Python function, capital distance. And then we can use this Wolfram function like a native Python function. And here we calculate the distance between Vienna and Canberra in Australia, which is nearly 16,000 kilometers of distance. But be aware that return types of Mathematica can be tricky, especially since Mathematica is a symbolic computation framework. So not all return values from the Mathematica, the Wolfram kernel, can be converted automatically to the corresponding Python objects. For example, if we define a function f, which is just x times the logarithmic function of x squared, and we then try to integrate this function between 0 and 1, we will get back the rational of -1/2, which is of type Wolfram language function. And with this return value, you cannot do anything with pure Python functions. What you have to do, you have to convert it somehow to a real numeric. Usually in Mathematica, you do this with the function n, and with this you get a return value of -0.5, which is a floating point and which can be converted to a native Python object or a Python variable, Python type. In addition, you can also use all kinds of Wolfram knowledge base. So you can trigger Wolfram Alpha from Python. Here, for example, I ask Wolfram Alpha for the moons of Saturn. So this goes to the Wolfram Alpha servers of Wolfram and retrieves the return value, which is an entity class. Obviously, this is again a Wolfram language function, so Python cannot do anything with it at this point in time. With the Wolfram function entity list, we can get a list of all the moons, which are quite a lot of Saturn, so that's over 80, I think. And like in Mathematica, we can then sort these entities by the class mass in descending orders and just list the first 4 of them. So that's why it's called big moons, and the biggest one is Titan at the end. And again, still, Python cannot do anything with it at this point in time. But what we, for example, if we just need the names of the moons, we can then use a map function and retrieve the names. So we get a list of strings, which can then be converted to a Python list of strings, with which we then can do further computation. So in the end, at some point, it can be a little bit tricky getting the results in the correct way so that you can use it further on in Python. What else? You can use also Numpy, pandas, and the Python image library with the Wolfram language, with some restrictions or some pitfalls. One I will show you in a minute. For example, Numpy, what I'm doing here is I import Numpy, I create the Numpy array and store it under data Numpy, so just standard stuff. And with this Numpy array, I then create here a list plot. So in the list plot command, I'm using a Numpy array, a Python Numpy array. Evaluate this list plot, store it under graphic Numpy. This is again a Wolfram language function I will get back. And then I use this Wolfram language function to export it to a PNG file, as you would do it in Mathematica with the resolution of 120. And in the end, I evaluate everything in here. So yes. And return value is the name of the file I've just created. And here I just load the image with Python commands to see what happened, and we see what we expect from Mathematica, a list plot of just this list of lists, more or less. So is it also possible with pandas? And here's a pitfall we have found. So we import the pandas as PD and then create a pandas data frame from this Numpy array. So we have here a nice table representation of this data. And what we, for example, can do, we can use the total function on this panda data frame. This works quite well. So here the sum of each column is calculated. So the first column is 20, the second column is 12, and so on. And now I'm doing the same list plot creation as I did before with Numpy, but now with data panda. So with the total Wolfram function panda data frames worked. Let's see whether list plot also works with it. And as you guess, it doesn't work. So what you have to do, so if you have a look at the graphic panda function, which is just the list plot, the return value of the list plot I've evaluated before, we see just the Mathematica command, graphics, and here should be the data points from the list from the panda data frame, and that's empty. So somehow these Wolfram, this WL factory function does not convert the panda data frame for list plot to the correct Wolfram language expression, but it does for a total, for example. So what you can do, what you have to do is again convert it. You can convert pandas to numpys, and then everything works out as expected. Yes. So in the end, yeah, there are some pitfalls and some restrictions, but most of the time it works out quite well using the Wolfram language out of Python. Yes, and in the end, you should terminate your session, and yeah, then you can check with stopped whether you have closed the connection to the Wolfram kernel and released it. Yes, with this, I've finished the second part of this webinar. And I want to come to the last part, which is the Wolfram language for Jupyter. There is a GitHub project from Wolfram Research to incorporate the Wolfram language directly in Jupyter. So you can use the Jupyter notebook interface as you have seen before, directly to communicate with a Wolfram kernel. So you directly execute your commands in Jupyter. And for this, you just have to clone the repository, change the directory into the created directory, execute this command, which adds the Wolfram language kernel to Jupyter. You can then have a look whether it's really available within Jupyter. So in my case, this was the output. Yes, and then you start your Jupyter notebook, and that's the second Jupyter notebook here. And as you see, within this notebook, we don't have any Python anymore. In the right upper corner here, you see the Wolfram language specified, so with the version number. So this is using really the Wolfram language. And here the commands are the same commands which you would use within, for example, Mathematica Desktop or Mathematica Online. And it works exactly the same way. So here I just clear the global namespace. Again, the installation directory of my Wolfram kernel and the version I'm running on. And these are more or less all the same commands you have already seen before. So select range, select the prime numbers from 1 to 100, integrate division through 0, which will not work, or integrate the function x times log x squared between 0 and 1. You can do even plotting. What you get back is a PNG file from Mathematica, so it's not really interactive. So if you do a 3D plot, you cannot rotate it as you usually can do within Mathematica. So that's a big downside. And also some other things don't work. You can use the Wolfram knowledge base as we have seen before. So we can again ask Wolfram Alpha for the moons of Saturn. We can show them, sort them again, and get back the name. So that's mainly the same thing we did in Python before. One big trade-off is dynamic content. So dynamic content does not work within Jupyter notebooks. So any manipulate or other dynamic content things, yes, won't work. What Mathematica will do, for example, for manipulate, and we will try this out, is it generates an animated GIF graph of the manipulate function and alters automatically the variables you manipulate between the minimal and the maximum value one after the other. The downside is that Mathematica has to generate a whole really a large number of pictures to generate animated graphics, and therefore this takes quite a long time, as you will see right now. So here we have just a nice function f, and we have here the derivatives with respect to the with u and v, and here we have a parametric plot of it. So you see it. So that's really nice function. And this manipulate usually this manipulate shows you this function and the plane of the two derivatives on this surface. So you can manipulate u and v from minus 6p to 0 and from minus p to plus p. And this really will take some time to calculate. I can show you in the meantime, hopefully, how it would look like in Mathematica. So wait a minute, sorry for that. Where is it? Yeah. So this is the same thing in Mathematica. I used the same kernel, that does not work. Sorry for that. Yeah, but we will see it in a minute. What's the result within Jupyter? Yes, with this, that's finally the end. Hopefully, I was not too fast in this webinar. We will, and I want to thank you. Obviously, at the end, I want to thank you for your attention. Thank you.